In the Beginning by Dr. Walt Brown. We are going to take a look at page 124, Crisis in Earth Science. The most perplexing questions, let me see here. The most perplexing question in the earth sciences today seldom arise. The most perplexing question in the earth sciences today seldom arises in classrooms and textbooks. What force moves plates over the globe? The single most difficult question that faces the theory of plate tectonics today is the same question that led to the downfall of Wegener's 1912 theory of continental drift. That is, what is the mechanism that drives the plate tectonic machine? The hydroplate theory gives a surprisingly simple answer that will be clear by the end of this chapter. It involves gravity, the Mid-Oceanic Ridge, Earth's core, and water. Lots of it. Be patient and read the next 37 pages carefully. A few of the mysteries: the Grand Canyon and other canyons. Mid-Oceanic Ridge. This 46,000-mile-long ridge discovered in the 1950s is the world's longest mountain range. It wraps around the Earth on primarily a great circle path. Unlike most mountains, it is composed of a type of rock called basalt. Because most of the ridge lies on the ocean floor, relatively few people know it exists. How did it get there? Why is it primarily on the ocean floor? Why does it intersect itself in a Y-shaped junction in the Indian Ocean? The portion in the Atlantic Ocean is called the Mid-Atlantic Ridge. Is it just a coincidence that it splits the Atlantic from north to south and is generally perpendicular to and bisected by the equator? If Europe, Africa, and Americas were once connected, how did they break apart? Cutting across the Mid-Oceanic Ridge is at almost right angles are hundreds of long cracks called fracture zones. Whenever the axis of the Mid-Oceanic Ridge is offset, it is always along a fracture zone. Why? According to plate tectonics, plates move parallel to fracture zones, but fracture zones are not always parallel. Sometimes they are many degrees out of parallel. How then can solid plates be bound by and move in the direction of these fracture zones? Can a train move on tracks that aren't parallel? Since the white arrows in figure 7 showing nearly intersecting fracture zones. Okay, let's pop out and see what we're looking at. Okay. In at least 8 places in the Atlantic and Pacific floors, segments of the Mid-Oceanic Ridge overlap for about 10 miles. They are called overlapping spreading centers. If plates are moving away from the Mid-Oceanic Ridge, then the distance between overlapping segments must be increasing. However, overlapping regions are always near each other, contradicting plate tectonics. Earth's major components. What accounts for Earth's oceans, continents, and their boundaries, shelves and slopes, crust, mantle, and core, inner and outer? Why are the shapes of the continental shelves and slopes so uniform worldwide? Low salinity water is being discovered far below continental shelves worldwide. Why would water, typically less salty than seawater, be found beneath the ocean seafloor? Ocean trenches. Concentrated on the floor of the Western Pacific are more than a dozen ocean trenches, long, narrow depressions, some of which are several times deeper than the Grand Canyon. Believers in plate tectonics claim that a trench forms when a continental-sized plate dives down into the mantle at a 30 to 60 degree angle below the horizon, a process they call subduction. How this dive begins is never explained. The initiation of subduction remains one of the unsolved challenges of plate tectonics. This would be similar to pushing a 30-mile thick shovel 1,000 miles into the ground. What force could do that? If subduction occurs, why do instruments detect almost no distortion of the horizontal sedimentary layers in trenches? Worse yet, if any plate reached a depth of only several miles, pressures would be so great that frictional forces would exceed the rock's strength. Therefore, sliding a relatively thin slab by pushing, pulling, or dragging would be impossible. This is similar to trying to push our 30-mile thick shovel down, now pinched in the jaws of a vise, down farther. It may break, buckle, deform, or crush, but it will, it will not slip. The next chapter will show how the deep faults are usually misinterpreted as subducting plates. Magnetic variation on the ocean floor. At a few places along the Mid-Oceanic Ridge, magnetic patterns on one side of the ridge are almost a mirror image of those on the other side. As you will see, the plate tectonic theory gained wide acceptance in the 1960s by also misinterpreting this surprising discovery. Some propose that these variations were caused by periodic reversals of Earth's magnetic field, although there is no theoretical understanding of how that could happen. Supposedly, if seafloor spreading occurs over millions of years, molten material moves away from the ridge and the magma solidifies, locking in the orientation of Earth's magnetic field at the time. Thus, a record of past flips of the Earth's magnetic field is preserved in rocks at different distances from the ridge, if the Earth's magnetic field periodically flips and the seafloor is spreading. That explanation is wrong, as detailed magnetic maps clearly show. No compass shielded from Earth's magnetic field would reverse direction whenever it crossed an alleged and misleading reversed band. However, as one moves across the Mid-Oceanic Ridge, magnetic intensities fluctuate. Someone merely drew a line through these fluctuations and labeled everything below this average intensity as a reversal. This is a false but widespread impression that these slight deviations below the average present magnetic fields that reversed millions of years ago. Calling these fluctuations reversals causes one to completely miss a more likely explanation. Although textbooks show these so-called reversals as smooth bands paralleling the Mid-Oceanic Ridge for thousands of miles, there is nothing smooth about them. Some bands are even perpendicular to the ridge axis, the opposite of what plate tectonics predicts. Also, the perpendicular bands correspond to fracture zones. The hydroplate theory explains these magnetic anomalies. See no seafloor spreading on page 186. A few lava flows show that rapid but limited changes in Earth's magnetic field have occurred. Lava cools at known rates from the outside of the flow toward its center. Magnetic particles flowing in lava align themselves with the Earth's magnetic field. When the lava cools and solidifies, the orientation becomes fixed. Knowing this cooling rate and measuring the changing directions of the magnetic particles within several solidified lava flows showed that at one time, Earth's magnetic field shifted rapidly by up to 6 degrees per day for several days. Note, this does not mean Earth's magnetic field flips every few million years. Submarine canyons. The ocean floor has hundreds of canyons, some that exceed the Grand Canyon in both length and depth. One submarine canyon is 10 times longer, 2,300 miles, so long it would stretch nearly across the United States. Many of these V-shaped canyons are extensions of major rivers. Examples include the Amazon Canyon, Hudson Canyon, Ganges Canyon, Congo Canyon, and the Indus Canyon. How were canyons gouged out? Sometimes 15,000 feet below sea level. Did ancient rivers or major drainage paths cut the canyons when sea level was lower or the ocean floor was higher? If so, why did these elevations change? Swift rivers supposedly cut most continental canyons. However, currents measured in submarine canyons are too slow, generally less than 1 mile per hour. Frequently, the flow is in the wrong direction. Submarine canyons that produce dense, muddy currents sometimes occur. However, they would not form the long tributary patterns that characterize river systems and submarine canyons. Furthermore, experiments with thick, muddy water in submarine canyons have not demonstrated any canyon cutting ability. Coal and oil formations. Why are large fossilized trees near the North and South poles? In Antarctica, some fossilized trees are 24 feet long and 2 feet thick. Nearby are 30 layers of anthracite, high-grade coal, each 3 to 4 feet thick. Buried redwood forests with trees more than 100 feet long and root structures showing that they grew in place are found on Canadian islands, well inside the Arctic Circle. Oil deposits are also inside the Arctic Circle. Was it once warm enough for trees to grow in the Antarctica or inside the Arctic Circle? If so, how could so much vegetation grow where it is nighttime 6 months of the year? Were these cold lands once a temperate latitude? Not according to plate tectonics. Each place places both regions near their present latitude when their now fossilized forests were growing. Methane hydrates. Some bacteria can live without oxygen. When they feed on organic material, they release methane gas, a combustible fuel. In 1970, vast quantities of methane, the largest source of buried carbon in the world, were discovered. Vast quantities of methane were discovered inside ice mixed with sediments lying up to 2,000 feet or more below sea level, but near coastlines. The ice molecules form microscopic cage-like structures, each encasing one or more methane molecules. The total energy value of this methane-ice combination, called methane hydrate, is at least twice that of the world's known coal and oil combined. Why is there so much methane buried along the coastlines? How did all the bacteria that produce the methane get there? And what was their gigantic source of food? The largest known deposit, named Hydrate Ridge, lies off Oregon's coast. According to plate tectonics, that part of the seafloor is sliding under North America and should be removing the methane hydrates. However, methane hydrates lie along all coastlines worldwide, whether those plates are supposedly subducting or not. Flaming ice. This ice burns because it contains methane, a flammable gas. How did that happen? Water freezes at slightly warmer temperatures than normal if it is under high pressure and contains dissolved methane. Such temperatures and pressures exist 2,000 or more feet below sea level. Thereon, under the deep seafloor, are vast methane deposits trapped in ice, primarily along the world's coastlines. How did so much methane get there? And what is the source, and why is it along coastlines? There's the methane. Flaming ice.